Let's look at what second derivatives tell us and along with their graph. So remember, the first derivative is the slope. So if the first derivative is negative and then it goes positive, somewhere in between there it had to have turned, meaning that we have our concavity, concave up, and how we can actually tell where our curve is concave up is where the second derivative equals 0. So we'll see that here in a little bit. But if I have my second derivative greater than 0, I have concave up. If I have my second derivative less than 0, I have concave down. So as you can see, these are kind of nice because this would let me find a minimum and a maximum. So if I knew I had a critical point here, all I'd have to do is check the second derivative to see if it's a max or a minimum. I point on the graph of a function where the concavity changes, so from concave up to concave down or vice versa, is called an inflection point. So if you remember, we had a critical point, and a critical point was where the first derivative equals 0. Well, here, for the concavity to change at a point, the second derivative must change signs at that point. And this is what we were using with our sign chart, but we were using the first derivative, but we can also look at the second derivative to see where the sign changes. So if I have, this is just like an xy point, just a value of c, and then I evaluate my function at c. If it is an inflection point of my function, then this c value is a partition number for my second derivative. So inflection points are where you're changing from concave up to concave down or concave down to concave up. And what we kind of like about these inflection points is they're actually where the slope is the steepest. Okay, it's either increasing the fastest or decreasing the fastest. And how we find this is where the second derivative equals 0. So we're also looking at to see if the second derivative changes signs, because remember, if it's concave up, the second derivative is positive. When it becomes concave down, the second derivative is negative. So it would have to change signs there somewhere. So for this function, let's find the inflection points. So I said you do it by finding the second derivative. So the first derivative, bring the 3 down, subtract 1. 2 times 6, 12, subtract 1. 9x is 9. And then the second derivative, I take the derivative again. 2 times 3, 6x, minus 12x becomes 12. And I want to find these factors, so I factor out a 6, and I set my factors equal to 0 because it makes it very easy to see. I can see that if x equals 2, then the second derivative equals 0. So x equals 2 would be an inflection point. So what I do with that is I can set up a sign chart with test numbers to the left of 2, like 1, to the right of 2, like 3, and I see if the sign changes. So I can see by the concavity, my second derivative from negative infinity all the way up into this inflection point is negative, so it's concave down, and then it changes signs. So it changes signs and becomes concave up. Now an inflection point is an xy value. So I actually want to find the y value, meaning I go back to my original equation, I plug in my inflection point 2, and that gives me my xy value, which is kind of nice because I can graph my original function and then plot that inflection point, and I can see certainly it's concave down, and then it's changing concavity right there, and then it becomes concave up. Just like with critical points, we said that there might be times the function's undefined or the derivative's undefined. So the same thing about inflection points is that it's important to remember that these partition numbers for the second derivatives are only candidates for inflection points. In other words, the function must actually be defined at x equals c, and the second derivative must change signs. So for example, if I have f of x equals x to the fourth, I find the second derivative, so the first derivative, 4x cubed, the second derivative, 12x squared. So the second derivative equals 0 just when x equals 0, right? But my question is x equals 0 an inflection point? Well, if I look at the graph, concavity is not changing there. So certainly this would not be an inflection point. And if you think about it, if you're plugging in values to the left of x equals 0 because of this being squared, even if they're negative, this is always going to be positive. And then, of course, positive values to the right of 0. So what we use inflection points for, and back to critical points and everything, is it gives us a way to do curve sketching, to just get an idea, graphing by hand, what my function looks like. So these are the steps for graphing a function with this curve sketching. First, we want to find the domain. Remember, the domains is typically the only time you have problem with the domains is if you're looking at dividing by 0 or you're trying to take the square root of a negative number, things like that. Find the first and second derivatives. The first derivative gives me that critical point. If I have the first derivative, I can look to the left and the right of the critical points and see where the curve is increasing and decreasing. My second derivative, I can then set equal to 0 and solve for inflection points. I can see if there's any place where the function's not defined, and then I plot everything. I might even plot x and y intercepts just so it makes it easy to connect the dots. So let's start with this function. X to the fourth minus 2x cubed. What's the domain? Well, I don't see any problem with plugging in any number. So the domain would be all real numbers, minus infinity to infinity. Find the first and second derivative. First derivative, second derivative. You got these shortcuts down, right? Find the critical points, which is where the first derivative equals 0. So set the first derivative equal to 0. Always look to see if you can factor. I can factor out a 2x squared. And then I set both factors equal to 0. So 2x squared equals 0. Solving it, x would equal 0. I want to find my y value, so I plug it back into my original function. 2x minus 3 equals 0. I add 3 to both sides. I divide by 2. So I get my critical point, 3 over 2. I want the y value. So I plug all in and go through all the steps. All I'm doing here is showing you how I get least common denominators and all that good stuff. So I did 3 halves to the fourth power, which is 81 over 16. I did 3 halves to the third power, which is 27 over 8. Okay, and then just continuing along, I went ahead and multiplied some of this stuff out, got common denominators. Okay, so this step, 27 over 8, I got the denominator of 16. And so I multiplied the top and the bottom by 2. Then I multiplied 2 times 54, and now I can actually subtract and get my 2 points. So my one critical point is at 0, 0. My other critical point is at 3 halves, negative 27 over 16. I can find where the curve is increasing and decreasing. We did this in the last lecture, where you take those critical points and you do your sign chart. So you pick values in each one of these intervals. I picked negative 1, 1, and 2. I plug these back into my first derivative because remember, positive and negative is my slope, so that would tell me if it's increasing or decreasing. Find the inflection point, so I get my second derivative. I set it equal to 0. I look to factor. I set both factors equal to 0. I see I get x equals 0 and x equals 1. So those are my inflection points. So my inflection point sign chart is based on my second derivative. 0, 1, I pick values in these intervals to see my concavity. If it's positive, it's concave up, negative, concave down. I want actual points, so I plug these numbers up here back into my original function. And so that gives me my inflection XY points to be able to graph them. Look for any asymptotes where the function's not defined. Well, this function's always defined for all real numbers. I might want to look at finding an intercept. Remember, the x-intercept is where your function or y equals 0. And then solve this for x. I could do some factoring things. I can see if that piece is 0, this is 0. If that piece is 2, this is 0. I plug these values back into my original function. So there's my x-intercepts. My y-intercept's a little bit easier. It's just where x equals 0. And so y equals 0 when I multiply all this stuff out, which gives me my y-intercept. Now I have all my key points. I have intercepts, which so nicely happens to be some critical points and inflection points, the origin. I have my other critical point, and I just put in some decimal here so I could plug it in to graph it, and my other inflection point. So I can kind of see just by looking at this, the function's going down. It goes flat, it goes back down, it goes flat, and it goes up. Why am I saying it goes flat? Because that's where the derivative's 0. Going down, goes flat. There's my critical point. It's concave up, it's changing to concave down. That's also an inflection point. Here's another inflection point. It's concave down, and it's changing to concave up. Here's my critical point where it goes flat, and then it heads up, and that's just my intercept. So we talked about critical points having a special meaning it's where the function goes flat, right, where your slope is 0, but it also helps you see where a maximum or a minimum would be. Well, inflection points have a special meaning. This is not only where the rate of change is going from increasing to decreasing, it's also where the rate of change, the slope, has a maximum value. And in business, this is called the point of diminishing returns, which it states that one input variable is increased. There's some point there which the marginal increase starts to decrease, which certainly that's something a company would want to know. They would want to know if they start increasing spending on advertising, you would expect sales to increase. But they would increase very quickly right away when you advertise, but then the increase would slow down. You'd start to see that slope start to level out. So the dollar amount, X, at which the rate of change of sales goes from increasing to decreasing, is called this point of diminishing returns. So, I mean, we could go ahead and continue and spend money on advertising, but I might see sales increase, but they're increasing at a slower rate. So let's see an example of this. We have a discount appliance store is selling 200 large screen TVs monthly. The store invests X thousand in advertising. So X, you can see my domain. I have up to 9,000 in advertising I can put in. And my monthly sales is given by this function. When is the rate of change of sales increasing and when is it decreasing? What is the point of diminishing return and the maximum rate of change of sales? So you need to learn to read these to see what are they even asking me to find. Well, if I want to know when the rate of change of sales is increasing and decreasing, I know that has to do with my first derivative. The point of diminishing returns in this maximum rate of change is my second derivative. So let's just go ahead and take derivatives. Okay, be sure you go through these and you see how I got my first and second derivative. How I tell when it's increasing and decreasing. I can look and find, I went ahead my first derivative and I factored out an x squared. So I can certainly see where critical points are going on. I can look at my second derivative and I can certainly see where inflection points are happening. And so with my first derivative here, if I plug in values, notice if I plug in anything from 0 to 6, this is always going to be positive. Even all the way up to a little bit less than 9, like 8, this is always going to be positive. And so my first derivative is positive, But what's happening with my second derivative, that concavity is changing. Notice my second derivative goes from positive, I'm just plugging in values like 1. Okay, so if I plug in a 1 here, you can see that this is positive. If I plug in a 6, this becomes 0. If I plug in like 7, this becomes negative, so it changes concavity. It's still, my function is still increasing, but it's not increasing as quickly. So let's look at the function, and we can see our inflection point here. Okay, I got my inflection point from back here by what would make this equal to 0, and you can see that it would be at 6. I found the y value, so it's concave up and it's starting to turn concave down. What this picture is the picture of the graph of the derivative. Remember, if I'm above the x-axis, that means I'm increasing. It's positive. So I can see that it's increasing, 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 increasing. This is the max that it's increasing. That's my inflection point. So that says if the store spends 6,000, 6 was in thousands, on advertising, monthly sales are going to be increasing the fastest at 524 TVs. The rate that it's actually increasing is 108 TVs per $1,000 spent on advertising. That's what the derivative tells you. So money spent beyond the 6,000 would still increase because my derivative is still increasing. I'm still above the x-axis. It's just starting to slow down. Notice my slopes. Remember, the derivative is the graph of the slope, so my slopes are starting to get smaller and smaller and smaller and smaller. Well, you can even see that from the graph, that if you drew a line, a tangent line here, and then you drew another one up here, it's starting to turn and not increase as quickly, which is important for businesses to know, because past this, they're going to start to see sales will still increase, but they'll increase at a slower rate.